In this video, we're going to define a mathematical structure known as a group and see how this builds on our knowledge of binary operations from the previous video. So we've got 4 axioms for a group to exist. The reason we're getting these is because there's lots of different mathematical structures that do follow these 4 rules, these 4 axioms. And when they do, if we can show that there's some theories that apply whenever these 4 rules are satisfied, we don't then have to prove each rule separately in each instance, because we already know that as long as we've got these 4 rules, then our theorems will work. So there's 2 points to this video. The first one is getting across how we are going to define this thing called a group, this mathematical structure. And the second thing is then giving some examples and also giving some examples of things which aren't groups to get a better understanding of how that's defined. So when we're defining a group, there's 2 things we need to know. We need to be given a set. In this case, I'm calling this set G. And we need to be given the binary operation. In this case, I'm calling it my binary operation star. I'm just drawing an asterisk for it. So this is talking really generally. If we've got some set of things, it could be the positive integers, it could be the real numbers, and if we've got some binary operation, it could be addition, multiplication, so on. As long as we satisfy these 4 rules, it's going to be called a group. So I'm going to talk through these 4 rules, and I'm going to add a little bit of information as we go through. So the first one follows on from what I mentioned in the first video, which is closure. If we have a binary operation and we're saying it's closed on G, what that means is saying that if we take 2 elements, so for any 2 elements, for all elements A and B belonging to some set G, if we do A star B, our answer will still be within G. So that's closure. So an example there would be if you take the positive integers and you perform addition, then when you do one positive integer plus another positive integer, you get a positive integer as your answer. So therefore it's closed because our answer is staying in the same set we started from. The second definition here, that star is associative in G, so associativity got defined in the previous video. This is just saying we only need it to work here when we're taking elements from the set G that we're defining, but this is saying that for all, if we take 3 elements, A, B, and C, from our set G, then it doesn't matter where we put the brackets. If we do A star B in brackets and then star C, that should give us the same answer as if we do A star B star C. This is the condition that normally we'll often take for granted, because if we're given multiplication, or if we're given addition, or if we're given matrix multiplication, you can just state that these things are associative. You're rarely going to be asked to prove those. You can just say matrix multiplication is associative, and therefore this holds. Obviously, if you've got division or subtraction, you should know from the last video those aren't associative, and therefore we're never going to have a group where our operations subtraction or our operations division. Now, the next 2 we didn't define in the previous video. One is saying there's an identity, so our third axiom is saying there's an identity element. Now, we're generally going to use the letter E to represent our identity element here. Now, what we mean by an identity element is we perform the operation, we might do E star some number, we're always going to get the same number back out. So in multiplication, an example makes more sense here. If we're just multiplying, 1 is the identity element, because if you do 1 times 7, you get 7 as your answer. If you do 7 times 1, you get 7 as your answer. If you do 9 times 1, you get 9 as your answer, but the multiplying by 1 doesn't change it. That's why 1's our identity element. If we're looking at addition, then 0 is our identity element, because if you do 0 plus 7, you get 7 as your answer. If you do 7 plus 0, you get 7 as your answer. So our strict algebraic way of writing this is going to be an identity element such that for all elements in G, so I'm going to say for all A belonging to G, we're going to have that if we do E star A, or alternatively, if we do A star E, we'll end up with still on A either way. doing the operation with e won't change our number at all. So just as an example here, like we were saying, if 1's our identity element and we're multiplying, if we do 1 times 7, that's the same as 7 times 1, it's just 7. 1 doesn't change it when we're multiplying. But that identity element is going to depend on what our operation is. And you don't have to use e for it, but that's the convention you'll see most often. Okay, the final rule we need, the final axiom we've got for groups, is that every element in the group has an inverse element. What this means, so I'll start off with an example again before we go algebraic. So in the case of multiplication, the inverse of 7 would be 1/7 because 7 times 1/7 gives you 1, which was your identity element. In the case of addition, the inverse of 7 would be -7 because 7 plus -7 gives you 0, which was our identity element. So what we're saying here is saying there's an identity element is saying that A inverse exists such that A inverse star A or A star A inverse gives us our identity element here. The key thing to notice is your identity element does have to be in your group. So if we were saying we were considering addition on the non-negative numbers, then 7 wouldn't have an inverse in the set because -7 wouldn't be in the non-negative integers. So when you're saying the inverse exists, that also has to be in the set you're starting with. This is a very abstract way of defining a structure. We're now going to look at it in practice because it makes more sense when you start getting into it. At the moment, we're very much in the weeds of it. There's one thing I want you to notice isn't in these rules, which is commutativity. We mentioned commutativity in the previous video, that A star B is equal to B star A. Now, we do give a special name to a group where our operation is commutative. So if our operation star is commutative, then we say the group is abelian. Sorry, I may be massacring the pronunciation there, but I'll spell it for you here. It's named after a Scandinavian mathematician called Abel, so maybe abelian. So that's another rule you just need to be aware of there. Another definition you need to be aware of, but that's not a requirement for something to be a group. Okay, let's look at some examples because it's the only real way of trying to make sense of these definitions here. So, the first example I want to consider is Z, which hopefully you recall is the integers, both positive and negative and 0, over addition. If we go through here, so if you're asked to check whether something's a group, go through these axioms one by one and check. So firstly, is it closed? So check of 1, well, if we take two numbers, A and B, both integers, then A plus B is definitely also an integer, so it is closed. So Z is closed under addition. So we've got our real one there. In that case, you don't really need to say much more. You can take it as a given that if you add two integers, we get an integer. There'll be some situations where we get on more complicated ones where we might have to go into more detail on those. The next one, associativity. Now we know addition is associative, so we can just state addition is associative and that's sufficient. You should make sure you get it written down, but you don't need to prove it as a result that you can just state as given. The third thing we want to check now is whether there's an identity element in this group. Now, if we're looking at addition, we're looking for an element that when we add it, it doesn't change the answer. So what can I add to 9? And I'm going to get the answer of 9. Well, add 1 to add 0. So there's a couple of things we want to stay here. So the identity element is 0, which does belong to our integers, and let's just explain why, since for all members A of the integers, we'd have that A plus 0 is equal to 0 plus A is equal to A, which is exactly what we want. So we've got the identity. We've got our third rule satisfied. And our fourth axiom now we need to check is whether there's an inverse. No, this doesn't even make any sense to ask until we've got an identity element, because an inverse element is saying, what can we do to get to our identity? Our identity is 0. So if I give you the number 12 and say, what do you need to add to get to the identity? You'd want to add negative 12 because that would get us to 0. So in general, for all members A of the integers, the inverse, in this case, is going to be negative A, which does belong to the integers. And we know it's this since A plus negative A is the same as negative A plus A, which is equal to 0, which was our identity. So we have our inverse here. You do want to be presenting this both times, even when it feels a little bit trivial. Just make sure you're covering that. Now, key thing which can easily be missed here is making sure you state your inverses in the group and checking your inverses in the group. That's often one that you can not consider and will catch people out there. So all of those four things are satisfied. So we can state that Z over addition is a group. And that's the way you'd present that, and that's the way you'd write that. So when you're writing a group, in brackets, first a set, and then the operation there. But just go through one at a time and get them. If you're trying to prove something's not a group, then that's much easier. If you can immediately see that one of those axioms isn't satisfied, you don't have to go through all four. If you're asked about subtraction and you know it's not associative, go straight and say subtraction isn't associative, and therefore this thing isn't a group. You don't need to check whether the other three hold or not. If one doesn't hold, the whole thing isn't a group. Now, in this case, this is a special group because addition is commutative, so this would be an abelian group. But here, I wasn't considering that. I was just seeing if it satisfied the axioms. Okay, let's look at another situation then. So what about if we go for a slightly tricky group here? And we might have to explain what we mean here. So I'm going to take the set. This time I'm going to take a finite set, the numbers 1, 3, 5, 7. And the operation I want to do is multiplication modulo 8. So as a reminder from the last video, what this means is we're going to multiply our numbers and then we're going to take the remainder when we divide our answer by 8 here. So on one of these, always start by getting yourself a Cayley table down. It'll make your life much easier to see exactly what's going on. So we write what our operation is here. Our inputs are 1, 3, 5, 7, so we've got it going both ways. Now, when we do 1 times 1, we get 1. So the top row is going to be easy to fill in. 1 times 3 is 3, 1 times 5 is 5, 1 times 7 is 7. Doesn't get much easier than that. 3 times 1 is 3. 3 times 3 is 9. Well, the remainder, when we divide 9 by 8, is 1. 3 times 5 is 15. The remainder, when we divide by 8, is 7. And 3 times 7 is 21. The remainder, when we divide by 8, is 5. And keeping on going here, we get 5, 7, 1, 3, and 7, 5, 3, 1. One way you can check here is you know multiplication is commutative, so check that you've got symmetry in that downward right diagonal there. If you don't, then you've probably made a mistake if you're dealing with an operation that's commutative. So now we've got our table, we can go through and check that everything comes out as expected. So rule 1 to check, is it closed? Well, yes, we do have that this set 1, 3, 5, 7. Sorry, I should write it as a set. Is closed under multiplication modulo 8 here because looking from our table, we can see that all the outputs are only 1, 3, 5, or 7. So as long as you've given your table, now you can just state for all A, B belonging to 1, 3, 5, 7, we have that A times B belongs to the set 1, 3, 5, 7, but you need your table to make that clear, Otherwise, it's not obvious you've got that. Note, if we had numbers 0, 2, 4, 6 appearing here, it wouldn't have been closed and it couldn't have possibly been a group. Second thing we want to check here then is whether it's associative. Now, same as before, multiplication is associative. And if we've got that, so multiplication modulo 8 is also associative. So we're all good with that. Third one to check is, do we have an identity element? Now, it's multiplication, so you might be able to predict anyway, but it's always worth checking with your table here. But yeah, we're looking for a row where this row doesn't change here. This row is identical, so 1 is our identity. So on 3, we're going to say that 1 is the identity element. I should make sure it states clearly that 1 belongs to the group we had. Well, that's fairly obvious that it does. And 1 multiplied modulo 8 by A is equal to A multiplied modulo 8 by 1 gives us A. So, sorry, my pen's gone a bit wonky there. So that's acting as we want our identity to. And final thing we want to check is, does everything have an inverse? This is probably the least obvious one of these in this situation. So we're looking, and in this situation, you do just want to list each inverse one by one. Now, 1's inverse definitely is just 1 because 1 times 1 gives us 1. That's what we're after. Now, what can we multiply 3 by, which gives us 1 as our answer in this table? If we look here, then when we do 3 times 3 modulo 8, we get answer as a 1. So 3 inverse is 3. And the same, actually, 5 inverse is 5. 7 inverse is 7. So these are actually called self-inverses. You don't need to write that down here, but if you hear about self-inverses, that's what we're meaning, that each element is an inverse of itself. That happens sometimes, you'll often see them, but it's not that common that every single element will be a self-inverse of itself. So, but what we can say here is, so every element has an inverse. In this case, you probably, once you've listed them here, you probably don't need to write any more. You can see from the table that's the case, and therefore we can conclude, yes, this is a group again. Let's just consider one that isn't a group so we can see what we might come up with otherwise. So final example, and this will be quicker when it's not because we only need to look for one thing that doesn't work. If we take the rational numbers over multiplication, why isn't this a group? Well, let's consider quickly. Is it closed? If we multiply 2 rational numbers, you're going to get a fraction as an integer of an integer, so yeah, it's closed. Is it associative? Yes, multiplication is associative, so this is still associative. Does it have an identity element? Well, if you multiply by 1, then surely nothing changes, although as we get to the inverse, we'll see we could object to that here. The problem is that 0, while 0 is in this group, there's nothing we can multiply by 0. If we do 0 times 1, we get 0. We don't get 1. Oh, sorry, so that still works for the identity. But when we consider the inverse, is there anything you can multiply? Remember, the inverse is saying if 1's the identity, we want to be able to do 0 times something is equal to 1. That doesn't exist. 0 does not have an inverse. So it's not a group. Just because there's one element there without an inverse is enough to stop it being a group here. If we went for the rational numbers excluding 0 over multiplication, that then would have been a group. We've solved one issue there, but we do need to be cautious about that, and 0 is often one thing that causes problems in there. Thank you very much.